Okay, in this problem we're given the voltage across a 0.1 Henry inductor. We want to compute the waveform for the current. If the current at t equals 0 is 0.1 amps. And then we want to determine how much energy is stored in the inductor at t equals 7 milliseconds. So here we're given the voltage waveform and asked to calculate the current waveform. So that's going to require us to use I of t as 1 over L, integral from 0 to t, v dt plus I of 0. And we will now need to find expressions for the voltage waveform over different intervals. And then we're going to go in and use this expression. So let's start off first with the interval from 0 to 2 milliseconds. Straight line, that's a straight line. Again, the equation is y is equal to mxb for a straight line. So if we start off, we look at the slope. It goes from 0 to 10 in 2 milliseconds. So the slope is 5,000. Now if we look, it's easy to see that the y-intercept is 0. So the voltage expression over this interval is 5,000 t volts. Now, the other intervals, for instance, 2 to 4, the voltage is constant at -5. From 4 to 6 is constant at -10. Then from 6 to 9 is constant at -5. I'm not going to write those down, but we'll come back to this waveform. Now, let's look at what happens to the current over the interval from 0 to 2 milliseconds. And we have I of t, we have 1 over L, which is 1 over 0.1, integral from 0 to t, 5,000 x dx, plus our initial value of 0.1. So that's just using 1 over L, integral from 0 to t, v of t dt plus 0.1. We pull the 5,000 out, this becomes 50,000, integral from 0 to t, x dx plus 0.1. So then I of t becomes 25,000 t squared plus 0.1 amp. Now we remember that the current through an inductor is a continuous function. The voltage changes, but we know the current doesn't change instantaneously. The initial condition for this next interval is going to be determined by, well, what is the inductor current at 2 milliseconds? So if we plug in, we'll have 25,000. We'll have 2 milliseconds. And if you do the calculation, that gives us 0.2 amps. So in our interval, the current goes from 0.2 to 0.1 amps. Now, if we look back at our waveform, we can see now from 2 to 4, the voltage is constant at -5. So now, to calculate the current waveform, we'll again use 1 over L, integral from 0 to t of v of t dt plus initial value. So we have 1 over 0.1. Now our interval starts at 2 milliseconds. And the voltage we can see is -5 dx. Now, here's our 0.2 that we just calculated. So notice we calculated that from the current expression because we have continuity of current for the inductor. So now we have -50 times the interval from 2 times 10 to the -3 t dx plus 0.2. So I of t becomes -50 times t minus 2 times 10 to the -3 plus 0.2. Okay, so there's our expression. Now, the inductor voltage changes at 4, but we know the current doesn't change instantaneously. So let's calculate the current at t equal 4 milliseconds. That will be the initial condition for our next interval. So then the current at 4 milliseconds then is 0.1 amp. Okay, so our voltage now goes from -5 down to -10, but we know our current is continuous, so that's going to give us, we just calculated our initial value for the next interval, so now let's do the calculations. So now we're integrating from 4 milliseconds to t. The voltage is -10. Here's the 0.1 that we just calculated. So now we have -100. We have the integral from 4 times 10 to the -3 to t dx plus 0.1. So now we have -100 times t minus 4 times 10 to the -3 plus 0.1. Now the voltage changes at 6. So we know our current is continuous. So we need to know what the current is at t equals 6 times 10 to the -3 seconds, because that's going to be our initial condition for the next interval. So then I of t equals 6 milliseconds is minus 0.1 amps. So that takes care of that interval. So there's the current, which will be, this will be the initial condition for our next interval. So again, remember our waveform now, it's -5. Okay, so from 6 to 9 milliseconds. Now we're going to have I of t is 1 over 0.1 integral from 6 times 10 to the -3 of t of -5 dx minus 0.1. So we have -50 times the integral from 6 times 10 to the -3 t dx minus 0.1. And now we get -50 times t minus 6 times 10 to the -3 minus 0.1. Now the waveform changes again at 9, and since the voltage is 0, the current's not going to change. So let's calculate the current at 9 milliseconds. And that gives us minus 0.25 amps. So now let's sketch the current waveform. It starts off at 0.1, and remember it goes to 0.2 in 2 milliseconds. And remember, this is a parabolic type waveform. Okay, so this is like a t-squared type. Okay, then at 4 milliseconds, it has come back linearly to 0.1. Okay, so this is linear. And if we look, the waveform from 4 to 6, and if we look at where that waveform ends up at 6, it was minus 0.1. So now at 6, we're at minus 0.1. Again, this is still linear. Okay. Then at 9, we wind up at minus 0.25. And then we stay there. So again, this is linear as well. So there's our waveform. Now, we were asked to calculate the energy at 7 milliseconds. Well, here's 7. So that means we got to go down here and calculate the value of the current at t equals 7 milliseconds. And we know that I of t equals 7 milliseconds. We'll have minus 50 times 7 times 10 to the minus 6, minus 6 times 10 to the minus 6, minus 0.1. Remember, this is basically we're using the expression valid between 6 and 9 milliseconds. This turns out to be minus 0.15 amps. So the energy then at t equals 7 milliseconds is 1/2 L, which is 0.1, times I squared, which is 1.125 millijoules.